Hello, hey, we are going to work on section 6.2. I'm calling it C because it kind of follows in order, and we're working with washer method today. So, what's the deal with washer method? Well, you can see here that we've got a couple equations that we're going to follow. So we've got the horizontal axis of rotation as well as a vertical axis of rotation. And I just want to try and scroll up here. And I'm still getting there. I'm not sure why I've got that message. There we go. So if I have this one, let's consider the x-axis as our axis of rotation. And if I have two curves, one curve looks like it's linear, the other curve is maybe quadratic there. And we want to take the region between those two curves and rotate it about the x-axis, it would come out looking something like this. Now, when I look at this x-axis, you can see right here's the axis of rotation, and there's a gap. There's a gap between the inside curve to the axis of rotation. Well, that's going to leave a hole in our rotational 3D object. And that whole hole is all of this region here. Okay, if you can visualize 3D, it really does help. So you can now kind of understand why this is called the washer method, because it looks like a washer that you'd put on a bolt. And in order to do a washer method, there's going to be two radii that are very important. And the first one would be from the outermost function to the inside curve, or I'm sorry, not to the inside curve, but to the axis of rotation here. So I'm going to go from the outer curve to the axis of rotation, and I need to get that length. Well, that would be some value of y then, wouldn't it? I put in an x where whatever that x value was there, and I come out with a y value. The other radius would be from the inner curve to the axis of rotation, and that's going to be much smaller, but that's what generates, it's kind of like I want to bore out that middle piece and leave that void so that we don't have volume going on there. So that's why it's called a washer method. And there's the two formulas for it. It's similar to disk method. If I just removed one of these, we're back to disk method. So essentially what we're doing is calculating the solid for the outermost radius, the larger radius, a volume for the inner radius, and we're subtracting that. So we remove that inner volume and it leaves the hole. We can do just like when we were working with disk, we can have horizontal rotation or we can rotate about a vertical axis. So let's do the first one. The first page, we're going to do horizontal rotation, and then on the second page, we're going to do some vertical rotations. It says find the volume of a solid rotated by revolving the region bounded by the graphs f of x equals square root x and y equals x squared about the x-axis. Sketch the graph, draw the representative rectangles, and on our way. So if I do the first function, square root function, 0, 0, and 1, 1 would be two points on that curve, and I know it'll look somewhat concave downish. The other function, let's put that one in blue, is going to be parabola shape. So this is y equals x squared versus f of x equals square root x. My axis of rotation is right along here. It's revolving about the x-axis, spinning about that. So now, see if you can identify the two radii. Let me see. I think I'm going to go with this, and I need to narrow that up a bit, though. So my outside radius would be found right along there. How do I calculate that length? Well, I could say r of x. And notice I'm using capital R because this one's going to be our large one. And I'm looking at top minus bottom to get that distance that it would be in y. My outer curve there is square root x. It attaches to this curve, which is really a y equals 0 equation line, so that would be 0. Notice that's our axis of rotation. Simplifying it, we get just simply square root x. Okay, on to the other one. Let's put this one in pink. The inside radius that generates the hole, or the hole of the washer, this would be our little r of x, whereas this was big R of x. So little r of x, looks like blue. Little r of x will be equal to, well, that curve, the top part of it's still top bottom, isn't it? I need to get the highest y value minus the smaller y value. And that function was the x squared function minus 0, because it comes back to our axis of rotation. So r of x equals x squared. Intersection points, I'm not going to make too big a deal on this one because it's pretty easy to see that they intersect at 1, 1. And if I put in here 1, I get out 1. If I put 1 in here, I get out 1. So it's really easy to verify that 1, 1 and 0, 0 are 2 points of intersection. So maybe even make a note to yourself. They intersect at x equals 0 and at x equals 1. Now for the volume equation. Volume equals pi integral from 0 to 1, those are our points of intersection, big R of x quantity squared minus little r of x quantity squared. That difference multiplied by dx will give us volume. So on our problem, we're going to integrate between 0 and 1. And the big R of x we had as square root x, that'll get squared, minus little r, which is x squared, dx. And then I'm going to do this one by hand. It's not too bad of 1. So I get x minus x to the 4th dx. Let's integrate. We'd have pi times 1/2 x squared minus 1/5 x to the 5th, evaluated from 0 to 1. Put 1 in first, and 1 squared will give us a 1/2. 1 going into the 5th power gives us a 1/5. 0, of course, is going to zero out on this one. And I'll get 5/10 minus 2/10, so I get 3/10 times pi. And there's your answer. So really very similar to disk method. Whoops, there's a problem there. Just we have an extra step because we had to remove the inner part of our 3D figure. Okay, the next one says we're going to revolve about a line y equals 1/2. And let's draw in our axis of rotation. Then down here at y equals negative 1/2. And then let's go put our functions on. We had 0, 0 to 1, 1. And that function was the square root function. And then I have the parabola function, y equals x squared. And we're going to rotate this now about y equals negative 1/2 instead of the x-axis. So that's going to elongate the big R's and little r. Big R is going to be from the top function to the axis of rotation. There's big R of x. And then let's go identify little r of x. I'm going to pop it right here. I could put it anywhere along here, but this just seems like a nice place to put it. I could have put it, way over here. I wanted to. It's just I need to go from the red curve, the inside lowest curve, to the axis of rotation. Okay, let me undo that one. All right, so now let's just do some calculating here. Big R of x. Still think in that top minus bottom format. So my top curve, once again, is square root x. Bottom curve is the axis of rotation, which is -1/2. So my big R in this case is a little more complicated than last time. It's square root x plus 1/2. Little r of x, little r of x. Little r of x will end up being the red curve x squared minus the lower function here, which is -1/2. It's the axis of rotation. And I'm going to get x squared plus 1/2 as my r of x. We know the intersection points are 0 and 1, so let's just go ahead and write our formula out. So volume equals pi. From 0 to 1 are our bounds. Big R squared. I have to write small to get this to fit. There's big R squared minus little r squared, x squared plus 1/2. And then I want to multiply, that is actually an area, I want to multiply it by dx. And that one is a lot more complicated, so I'm just going to put it in my calculator to calculate that out. And let me bring up my calculator. Oh, if I could find my mouse. There we go. And what I would suggest is putting your functions in. I'm going to make this my y1 function, and I'm going to let this be my y2 function, so that then I can go to my home screen and set the integral in there, noting that y1 gets squared and y2 gets squared. So final answer ended up being 1.990. So practice that. Use your calculator. Homework today is on Delta Math, and that is asking for 3 decimals of accuracy. So definitely use your calculators today. You do not have to integrate by hand. Okay, example 2. I wanted to do one that was different, where we had the axis of rotation here lying below the shaded region. And this one now I'm moving the axis of rotation to above the shaded region. Sometimes people do have a little bit more difficulty with this one. So here's our axis of rotation at y equals 8. We're rotating about that one. And what are our functions? We got a square root function and a linear function. Oh, those should be pretty easy to identify, shouldn't they? Okay, so square root function is f of x equals 3 square root x, and my linear function is g of x equals 3/2 x. Where do they intersect? We probably are going to have to locate that. Actually, it looks like they intersect at 0 and 4, doesn't it? And, yeah, well, let's go ahead and do that right now while we're talking about it. The intersection. I'm not positive that it's 4, but I want to confirm that it's 4. So I'm just going to look at what is f of 4. F of 4 would be 6. And g of 4, I'm hoping it's 6 so that it's an easy intersection point. And I'd have 12 divided by 2, so yes, indeed. They definitely intersect at 6, or x equals 4, y value of 6. And then if I checked out 0, I do get that each of the functions intersect at 0. So I've got my intersection points at those 2 values. So now I know the bounds of my function. Let's calculate big R and little r. Okay, so big R. Big R. I need the outermost to the axis of rotation. So big R of x is that top minus bottom because we're working in x numbers, values. My top function is the axis of rotation this time, which is 8. And it goes until I reach the outermost function, which is the linear function, 3/2 x. Then let's go find little r. I'm going to start at the top again. Oops. Little r of x. Once again, top minus bottom. And that's going to be 8 minus, well, it'll extend to the inner curve to get the small radius. There's little r. Here's our big R. And little r is the square root function, 3 square root x. If you can get those two things, that I think is really the hardest part of doing volume of rotation washer method. Now we're going to get volume equals pi integral 0 to 4 were our intersection points. I need big R squared, 8 minus 3/2 x, quantity squared, minus little r, 8 minus 3 square root x squared. And then I need to take that and multiply it by dx. I'll slide it right there. Another good one to use on your calculator on, and I have an answer for you. It is 125.664. Okay. Once again, I would have set this equal to my y1, this equal to y2 in my calculator, and then calculated the integral. Example 3. Now we're going to switch to a vertical line of rotation. So here you can see our axis of rotation. And maybe I should read, huh? I've got two cases for us. We're going to do A and B. In this one, I've got the axis situated off to the right. Find the volume of the solid rotating the region about the line x equals, a region bounded by x equals 6 minus y squared, and x equals negative y, so that's going to be a linear function, about the line x equals 8. So we just picked up that this is x equals 8 for our rotational position. And then we've got the two other functions. We've got the linear function, x equals negative y, and we have, let's put a different color on this, we've got the quadratic x equals 6 minus y squared. And notice that they did us a favor. They already have our function set up as x equals, it's all in terms of y, which we must have if we're doing a vertical rotation. All right, so the region that we want to rotate is this. We want to rotate it about our line here. So that would be kind of a weird looking shape, wouldn't it? Let's talk about big R. So big R can be found by going right minus left. I want to go to that outermost function, and that looks like the linear is the farthest to the left. So big R of x is equal to, now that we're working in y's, you've got to think in your brain right minus left, because this is going to be some change of x value. We want the distance in x. So that's right minus left. Alrighty, right function. Well, that's x equals 8 minus my linear function, negative y. So I get 8 plus y for the big R. The little r is axis of rotation to the innermost curve, which would be the quadratic curve in this case. So here's little r. Back to here, this was big R. So little r of x will be right minus left again. And that will be 8 minus 6 minus y squared. Note the parentheses because that we need to subtract both terms of the leftmost function there. So I'm going to get 8 minus 6. Oh, let's just write it as 2. 2 minus minus makes plus. I get 2 plus y squared from my little r of x. Awesome. Now I'm almost ready to go and calculate the volume, but I don't know my intersection values. So let's calculate intersection. I hope I have room here. Intersection. So the intersection value will be where the two functions meet. 6 minus y squared equals negative y. Set the two equations equal. I want positive y squared to factor, so I'm going to add it to the other side and bring that 6 over, which would be subtraction as well. So I'm going to end up with y squared minus, oh, this is factorable. Nice. Y minus 3, y plus 2. Give me a y equals 3 and a y equals negative 2. Believable, right? This looks like it has a height of negative 2, and this other intersection looks like a height of 3. So I'm jiving with that. That looks good. All right, let's go calculate now the volume. Volume equals pi integral from negative 2 to 3 big R of y squared. Oops, right for me. Let me try again. Big R of y squared minus little r of y squared, all multiplied by dy. So in terms of r's, I would have big R, 8 plus y squared, little r, 2 plus y squared, squared, dy. See if I can get those extra brackets in there. And another good candidate for a calculator, 785.398 cubic units. Not sure what these were measured in, but we know volume, b units cubed. All right, so that had the axis of rotation off to the right. Next one, let's move it to the left. So my axis of rotation on the left side here is going to be right here. And what is the function? It looks like it's about the line x equals negative 9. We've got the two functions. Let's set up what the longest r would be. Think right minus left. So big R of x is going to equal right minus left. And the right function to me appears to be that linear function. So, just trying to think of what I want to use for. I'm trying to thin it up, you guys, so that it isn't so thick. All right, green. Right minus left. This will be big R of x. And that will end up looking like our linear function. 2y minus my axis of rotation, negative 9. No, axis of rotation here. Where on the other one, we led off with axis of rotation because it was farthest to the right. So it's not always axis of rotation that is your second function or value that you're subtracting. This will give us an r of x equal to 2y plus 9. Okay, hold on to that. We'll need that one. And then let's switch over, and we used green. Let's use purple. Inside function, to axis of rotation would be big R, or I'm sorry, little r of x. Right function minus left function, still on that. Right minus left when you're working in y's. Oh, and why am I not writing in terms of y? Switch that up, just caught that, big mistake. Those are all y values there. R of y, R of y, R of y. Okay, we got that figured out. Whew. All right, right function, that is that square root function, this guy. -8 plus y squared, take away the axis of rotation, which is on the left, -9. Gets me -8 plus 9y squared plus y squared. Looks like I end up with 1 plus y squared. We also need to know where these points of intersection are. So let's get an intersection going here. Intersection. Set the functions equal. -8 plus y squared equals 2y. I'm going to bring everything to the left side this time. Factoring, I get y minus 4 and a y plus 2. Hopefully you're getting so fast you can just do those. You just see them, don't you? Y equals, you do enough factoring and you kind of get a real good feel for it. Does this look like it has a height of 4? Yeah. Does this look like it's down at -2? Yes, for y values. All right, now, I don't have a lot of space. We're going to try and squeeze volume in here. I'll do my best. No promises. All right, volume equals pi. Integral 4 to -2, big R squared, 2y plus 9 quantity squared. Take away little r, 1 plus y squared, squared. And that stuff gets multiplied by dy. An excellent candidate for calculating in your graphing calculator to get our final answer. Okay, so there's a good look at washer method today. I hope it makes sense to you. They are a little bit harder to sketch for sure. Yeah, I mean, I could try to imitate this. I don't know if I even should try. Here would be that outer function, that inner function. I'm just trying to get their reflections so that we could draw in a representative washer. Here would be the inside of our washer, that inside hole. And then I'd have this outer hole, or outer ring, not a hole. And then you'd have that thickness coming through here. And this would be the solid edge of our washer. And then maybe if I can try to widen that's that perspective you see. There's what we're doing, and we're just stacking a bunch of washers side by side to get their volume. You can see how our axis of rotation was the x-axis. There's little r, and then extend all the way out, and then you're talking big R. Okay? So have a good day. Homework is Delta Math. Go look for it. It is due in a couple days. Thank you.